Okay, guys, welcome back to our channel. Right, for the new subscribers, please, if you're watching this channel for the very first time, please kindly hit the subscribe button below and then turn on the bell notification icon. It helps us to, it motivates us to record more videos for you guys. And for those persons that are coming back to watch our videos, thank you very much for your continuous support, because if you guys don't watch the video, I don't think I'll be encouraged to do more. So thank you for always coming back to watch the video. All right, in today's class, today's video, I'm going to be explaining experiment 2. Sorry it's coming late because I had to compare and contrast so many values. All right, it has not been really very easy, so you have to get values from here and there and then compare and contrast. All right, the experiment is experiment 2, which is separation of mixtures. That's the title of the experiment. Now, the objective of this experiment, which doubles as the aim, is to separate a heterogeneous mixture based on the chemical and or physical properties of each component. The apparatus we made use of, based on the information I gathered so far: beaker, evaporating dish, weighing balance, aluminum oxide, calcium carbonate, and calcium. This is not calcium chloride, but instead copper sulfate. All right, so you can actually add up any other one you think you guys made use of in the lab. Okay, so the list is endless, and do not forget to add your dates. Very, very important. All right, now this should be on your data sheet. Okay, now let's look at the data sheet. Now, if you actually noticed, these are the values I got from people that conducted the experiment. The sample, in this case, the sample, okay, the sample, of course, is the mixture we're talking about. The sample is the mixture of these three components: Al2O3, CuO4, and calcium carbonate. Now, let me quickly run through these three compounds based on what they stated in the manual. Now, this makes up the sample. So anytime I say sample, anytime I'm referring to the sample, I'm talking about these three combinations together. All right, so our aim is to separate this this mixture. They are heterogeneous because their composition, how will I put it now, they don't really have the same phase. Their sizes are not the same, even if three of them are solid. Okay, now the mass of the beaker plus the sample, right? The mass of these three of guy plus beaker, all right, now give us this. But before we come to this, the beaker itself, the beaker, now the mass of the beaker when it was empty was 51.75. Let me state this. Now, you see the mass of these beakers, it doesn't really matter, right? What matters is the mass of the content before, like the mass of the content is after minus before, right? You can use anything to measure any compound at all, but at the end of the day, it is a content of that guy that I'm interested in. Some persons, their beaker, this value might be higher than 52.78. I don't think they'll really penalize or pay much attention to this. What they really care for is the calculation part, right? Because I learned that some persons made use of 100 ml beaker, while some persons, other persons made use of 250 ml, right? So your value, if your value is not corresponding to this, there are two options. You can decide to copy everything I have here, because this is actually the value I got from one person in the lab, and based on what I'm hearing, most persons did not conduct the experiment. You were asked to get data from your colleagues. So even if you decide to recopy everything here into your manual, you will not be penalized. Yes, you will not be penalized. So instead of you to copy what you're not really very sure of, I can actually assure you that this will still get your mark. So the mass of the beaker when it is empty is 51.75. Now when we added the sample, remember the sample is a mixture of aluminum oxide, copper sulfate, and calcium carbonate, right? When we added the mass of this and weights again, we got 52.78. Now Now let's take off this. I made this very easy for us. All right. Now we've gotten the mass of the beaker and sample to be 52.78. We have the mass of the beaker to be 51.75. All right. So I said therefore here. So therefore, the mass of the sample will be mass of the beaker and sample, which is 52.78 minus the mass of the beaker when it is empty, which is 51.75. So this becomes 52.78 minus 51.75. Now the answer here is 1.03 grams. All right, so the mass of the sample is 1.03 grams. All right, now we proceeded to the next stage. Remember they told us to weigh the evaporating dish when it was empty. Of course, they will give evaporating dish. Right, now remember our sole aim is to separate a mixture. Let me show something. I have copper sulfate plus calcium carbonate plus Al2O3. The title of this experiment is separation of mixture. So I want to separate these three guys. And the first thing they did to separate this copper sulfate is soluble in water. That means if you dissolve it inside water, it's going to dissolve into the water. It's more like adding salt into water. The salt is going to dissolve into the water. All right. So this guy is insoluble. This guy is also insoluble. So what they did was to first of all separate these copper sulfates. They added water to this guy, and the whole of this dissolved into the water. Do you understand? I'm actually carrying out the procedure here. They dissolved these three guys into the water, and this was actually dissolved. This did not dissolve. Calcium carbonate did not dissolve. Aluminum oxide did not dissolve. So after they must have dissolved this, they decanted the mixture. Decantation simply is more like you're soaking gari, right? You pour water into gari, and then you actually want to pour out the first part that contain those particles of gari that you do not really like. So that's decantation, where you separate the liquid from the solid in such a way that the solid will not follow the liquid and pour out while you're pouring out the liquid. Okay, so that is a process they use in eliminating this guy from this composition. But I wouldn't want to be going to the practicals proper. All I just want to do is to carry out the calculations. All right, so we've actually gotten the mass of the sample, which is 52.78, the mass of the beaker plus the sample minus 51.75. Remember, the mass of this sample is the mixture of aluminum oxide, calcium carbonate, and copper sulfate. Okay, now for this second guy here, mass of evaporating dish and dry calcium chloride. Now, like I said, this is not the time for me to start explaining these procedures. It's basically for calculation. All right, so how did we get this particular guy? Right, after we must have added water to the mixture to eliminate copper sulfate, because copper sulfate will dissolve into the water. So when you pour out the water, you now have aluminum oxide and calcium carbonate. All right, now this is the two that is remaining. Now we have removed this from addition of water. Right, now when we added HCl to the mixture, these two mixture that is remaining, this HCl is going to react with calcium carbonate. When it reacts with calcium carbonate, we're going to have Ca plus HCl. Now this is what we're going to have, CaCl2. I'll put 2 here and I'll put 2 here, plus CO2 plus water. All right, so we want to now separate this calcium carbonate from aluminum oxide. We added HCl because HCl will only react with calcium carbonate. Remember, the first thing was for us to remember this topic is separation of mixtures. So we have 3 mixtures. The first thing was to remove copper sulfate by adding water. When you add water, this entire copper sulfate will be dissolved into the water. And when you pour out the water goes alongside with the copper sulfate, leaving behind aluminum oxide and calcium carbonate. Now for me to remove calcium carbonate, I will add HCl. The HCl is not going to react with aluminum oxide, it's just going to react with this. And when it reacts with this, it's going to form calcium chloride. Yes, it's going to form, sorry, this 2 is not meant to be here, pardon me. It's going to form calcium chloride. So the mass of this calcium chloride, how are we going to get it? All right, this calcium chloride will be formed with water. All right, will be formed with water. So I wouldn't want to go through the entire process. All right, so if we read through the procedure, we're going to understand this guy much better. But let me just stick to the calculation proper. All right. Now, the evaporating dish, the mass of the evaporating dish when it was empty gave us this 34.39. Class, listen up and listen very carefully. I'm seeing some persons work here, they use beaker and they were getting 98.7 something, 98 point. You don't have to worry yourself. If I had made use of 98 point this, that simply means you don't have to worry. That was what they gave to you guys to carry out your experiment. But the mass of this calcium chloride you're going to get should be very similar to those persons that made use of evaporating dish of this mass, right? Now, if you look at this, the mass of the evaporating dish when it was empty is 34.39, which is this. Now, when we actually added the dry calcium chloride, after you must have evaporated the water out of it, you now have dry calcium chloride. Now, this becomes 34.69. So you say 34.69 minus 34.39. So here is going to be 34.69 minus 34.39. Now this becomes 0.3 grams. So here is 0.3 grams. All right. Now, the mass of calcium carbonate. Remember, calcium carbonate, when we added HCl, this guy gave rise to, calcium chloride plus water plus CO2. Okay, so whatever, if from here 1:1 ratio, do you understand? So whatever the mole of this is, that will be the same mole of this. If you carry out the calculations, you're going to get the answer. So instead of it to go through these parts, these stress, they even made it very simple for you guys. They said this number 6, mass of calcium carbonate in the original sample, is the result you are going to obtain from this, which is 0.39 times 0.9. This 5, you're not multiplying 5 with this. Result from 5, the result from 5 is 0.3. Right, so 0.3 times this. So I'm going to come here to say, I'll cancel this. Right, this is going to be 0.3, the results I obtained from carrying out calculation number 5, times 0.9. So here becomes 0.27. Here becomes 0.27 grams. So the mass of calcium carbonate is 0.27 grams. All right. Now, if you realize that based on this, we have succeeded in removing CuSO4 by adding water and this guy dissolving. Now, we succeeded also in removing calcium carbonate by adding HCl. So what is left now is Al2O3. So we now say the mass of the beaker plus the remaining solid, right? Remember, this beaker plus the entire sample was 52.78, all right? Now, when we now remove copper sulfates and calcium carbonate, leaving behind just this guy, what we now got is 51.66, exactly. So therefore, I now come here to say, although they did not make space for us to record mass of aluminum oxide, but if you look at the next page here, we are asked to give the percentage of this. So for you to give the percentage of this, you will say mass of aluminum oxide all over the total mass times 100. So it's important we know the mass of this. So that is why I made this this particular writing here. Mass of aluminum oxide equals to mass of beaker and remaining solid, which is this guy, minus mass of the beaker when it was empty, which is this. All right, so this becomes equals to, okay, so Please, the value for the mass of beaker and the remaining dry aluminum oxide is 52.06. I just had to verify that again from the notebook. 52.06. Remember the mass of calcium carbonate 0.3 times 0.9. This 0.3 was what we got from number 5, and the instruction here says the mass of the answer we obtain from 5 times 0.9. Okay, so this is, we got 0.3 in number 5, so when we multiply with 0.9 we got 0.27. so this is equals to 0.27. Okay, so like I said, we actually had to verify that guy again. So here, the mass of the beaker and remaining dry solid, which is this guy, the remaining dry, remember we had a mixture of, I already explained this, we had a mixture of copper sulfate, calcium carbonate, aluminum oxide. We remove this guy by dissolving with water. So once you dissolve with water, the entire CuSO4 goes alongside with water. We remove this guy by reacting with HCl. So the moment you react there with HCl, this will be converted to calcium chloride, right? All of them, and then you weigh, and then you actually dry, leaving behind this particular young man here. Recall, we actually, separated this using addition of water. We separated this using addition of HCl. So what we have left is the solid of this. So the value we have after after weighing it again, we have 52.06. So we say the mass of aluminum oxide is the mass of the beaker plus remaining solid, which is this. So we say 52.06 minus the mass of the beaker when it was empty, 51.75. So this becomes 52.06 minus 51.75 is equals to 0.31 grams. Okay, so we've gotten the mass of aluminum oxide to be 0.31 grams. All right, we want to get the mass of this so that we can fill it up here. Now remember this in the mixture, sorry, let me come back here again so that you understand very well what we have here. Now the mixture comprised of CuSO4 plus Al2O3 plus calcium carbonate. Now when we added water to this, right, the color of this copper sulfate is always white, but when we added water to this mixture, the purpose of adding this water was to dissolve this. So the moment we add water to this guy now becomes CuSO4.5H2O. The color becomes blue. The color of this guy is always blue. Obviously, you're going to observe a blue color if you actually conducted this experiment. Now, when we decanted, right, we actually moved out the entire mass of this out from this mixture. How did I know that? Now, the moment we added water, anytime once there is CuSO4 present, this guy will turn to blue. So after adding water to this mixture, any blue color you actually experienced or you saw was as a result of copper sulfate. So when you take out the entire copper sulfate out of the solution, you're no longer going to see blue color again, such that if you add water subsequently, the blue color will fade away, meaning that the entire copper sulfate has been taken out. All right, so them asking you to solve for copper plus 5H2O is equivalent to asking you to solve for just that of the sulfate, because the water was decanted. You actually poured away the water. So the mass of this in the original sample is going to be the mass of the sample. Mass of the sample, we got it to be 1.0 from this first calculation. This is 1.0 minus, all right, now mass of calcium carbonate. From here, we got mass of calcium carbonate to be 0.27 plus mass of aluminum oxide. From this calculation, remember aluminum oxide was actually part of the mixture. So mass of calcium carbonate plus mass of aluminum oxide, this is 0.31. All right, now for us to actually get this, we'll now say, sorry, so we're now going to say 1.03 minus, so this is 0.58. So the mass of this becomes 0.45 grams. So that is how we got 0.45. So this becomes the mass of copper sulfate pentahydrate. So we actually bring down the table so that we can have a look at the table. So this is, we have gotten the value. Now moving down to the calculation part, right? Now we actually said for the first one, this is what we're going to do. For the first one, we'll say mass of original sample is 1.03 grams. Okay. Now for number 2, percent aluminum oxide in sample is equals to mass of aluminum oxide all over mass of original sample times 100. So this becomes the mass of aluminum oxide. We got this to be 0.31. So this becomes 0.31 divided by 1.03 times 100, because they said percent, so we have to add 100. So we have 0.31 times 100 divided by 1.03. So we have this to be 30% approximately. So this is 30% approximately. Okay. All right. So I'll quickly clean up this. You can actually pause the video and then check it out. So I'll come back here. I'll say, now let's look at that of say number 3. Percent calcium carbonate in sample. Now this is mass of calcium carbonate all over mass of original sample times 100. Okay, so calcium carbonate is actually this number 6. We got this guy to be 0.27. How? Mass of calcium chloride was 0.3, but they told us for us to get the mass of calcium carbonate, we got multiply whatever we have as number 5 times 0.9, and that gave us 0.27. So this is a mass of calcium carbonate. So we'll come here, we say 0.27 times 100. Now the mass of the compound is 1.03. Now this is approximately equals to 0.27 times 100 divided by 1.03. So this is 26% approximately. Yeah, so this is 26%. Okay, so how do we get that of the So the last one is going to be percent CuSO4 equals to mass all over the original mass of sample, which is this 1.03 times 100. Now, what is the mass of copper sulfate that we got? The mass of copper sulfate that we got was 0.45 or 0.45, this guy. All right. Now, so which is the same thing as what we have here. So we'll come here, we say 0.45 all divided by 1.0 times 100. Okay, so let's see what we're going to have here. So this becomes 0.45 times 100 divided by 1.03. So this is approximately 44%. Approximately 44%. So we have 40, it's 43.6, but which is approximately 44%. So come here, we'll say 44%. Now, if you add up these three guys, 30 plus 26 plus 44, that gives us 100. That means the mixture of Al2O3 plus this. Now this guy contributed 30%, this guy contributed 26%, and this guy contributed 44%. Okay, so that's that for the calculation. Although we have some few questions we're going to answer here, but I already actually answered the question. So if you read it out, it's self-explanatory. So for this first one, they said if some of the calcium carbonate in part 3 reacted with HCl, how will the inherent error affect the reported percent composition in A? Now recall that I said this will not affect the reported percentage of this. Why? Because remember, before we added the HCl, we had earlier added water. The water dissolved copper sulfate, and then we decanted the copper sulfate. So every single thing here was already moved out of the mixture before we added the HCl. So that's why I said this will not affect the reported percentage of this, since it was already separated via decantation from the mixture even before the addition of the HCl. Okay. Now, how do you explain now this? I said the percentage. Now remember that the addition of the HCl was to actually react with calcium carbonate, and that reaction gave rise to calcium chloride, CaCl2. So that means the more calcium chloride that would be formed solely depends on the amount of calcium carbonate that will react with the HCl. So if more of the calcium carbonate react with the HCl, more of calcium chloride will be formed, right? So if more of calcium chloride is formed, that means the mass of calcium carbonate we're going to get from our calculations will be higher. Now look at what I said here. I said the percentage composition will decrease because they asked us if some part of this did not react. So if some part of it did not react, that means the calcium chloride that will be formed will actually reduce as well. So we said the percentage will decrease since the mass of calcium carbonate, calcium chloride that would be formed would be lower. The more of calcium carbonate that will react with HCl, the greater the mass of CaCl formed, and the greater the mass of this, and vice versa. If some of the calcium carbonate react, it means that mass of this will be formed lower. Like I meant to say, the mass of this form will be lower. You can restructure this English. Remember, this video, you're not the only one watching this video. As many persons as possible will actually love to watch or will be watching. So it is to your own best interest you actually rephrase the statement and then understand what I'm trying to say and perhaps put it in your own language or writing. It wouldn't really make sense that more than 15 manuals will be having the same write-up. All right. I said if some of this reacted, it means that mass of this form will be lower. The mass of CaCl lower too, since the mass of this is obtained via this. Recall that the mass of CaCO3 was obtained from the answer we got from CaCl2 times 0.9. So if this guy is high, you multiply with this, you're going to get a high calcium carbonate. Okay. All right. So for this guy, for the C part, we said the percentage. Remember, if let me clean up this. Now for the C part, they said what would be the effect of that guy on aluminum oxide? Now let me explain something. We have a mixture, three mixture: copper sulfate, calcium carbonate, and aluminum oxide. The copper sulfate was separated by adding water and then decanting. Once you add water, copper sulfate dissolved in the water, you pour it out, the water goes alongside with the copper sulfate, leaving behind calcium carbonate and aluminum oxide. You added HCl and the HCl reacts with calcium carbonate. Now, if some of the CaCO3 fails to react with the HCl, right, they will actually add up to the mass of the aluminum oxide that will be remaining. So that is why I said the percent composition will be higher. Why? Because they asked us if some of this, if some of in part 3 reacted, some, not all. If all of them reacted, that means they will not add up to the mass of this. Remember, this guy, from what they said the mass of beaker and remaining dry solid. So if that calcium carbonate did not react completely with the HCl, some of them will add up to this aluminum oxide and then increase the mass of this. And when it increases the mass of this, it will also increase the mass of aluminum oxide that will be formed. So that is why I said the percent will be higher, since the unreacted mass of this will add up and form mass of remaining dry solid, hence increasing the supposed mass of aluminum oxide and its percent as well. Okay, now look at this in part 2 and 3. Explain why it is necessary. Now just carefully look through this answer. And of course, if you add water, right, water is going to dissolve all the copper sulfates, convert them to blue color, which will eventually pour out, right? So addition of this water will minimize relative error that would likely occur during percentage composition. If the water is not added, right, how would we be able to separate the copper from the mixture? And if we are not properly, if we are not able to properly separate the copper from the mixture, it simply means that it's going to affect our recording, our weighing values, and of course it's going to lead to error, right? Expected value will actually differ greatly from what you're expecting, right? So when you subtract the expected from the actual, the value will be high. So I already explained this here, so you can quickly run through this. And please, right, if you actually are not on our group chat, Delzy and Y tutorials, please make sure you try and join, because if you have any questions, my WhatsApp is actually available. All right, so just text me on WhatsApp and I'll be there to answer your question, right? For those persons that may be asking, Sir Delzy, what is your WhatsApp number? Of course, I'll display it on the screen. Please make sure you ask your question. All right, thank you very much. Please hit the subscribe button for those persons that are just joining us for the first time. Thank you very much.